Yeah. So yeah, sorry for that. I forgot to record the first 4 minutes, but thanks who NS, I believe. So he reminded me I started recording now. I was talking about, for those, just to remind, I was talking about why we're using console, why it is kind of irrelevant, which software we use, and what's the aim of this tutorial, and so on. So if I go back, this is the opening screen of console. We have a model wizard and a blank model. To create a project, you can start from nothing like a blank model, or you can just select one of the available models in console. So it's easier to go with the model wizard option. And we have like 3D, 2D, 2D axisymmetric. So what kind of geometry we'll be working with? The most general one is 3D, but many problems can be studied in lower dimensions. Even 0D is possible. I don't really know what it means. We have to see the documentation. But today we will be doing some 2D. So I selected the 2D one. It was a bit quick. So I selected a 2D model. I will do a two-dimensional analysis. And then we have lots of physics that we can select. So I recently used, while preparing myself to today's tutorial, laminar flow, turbulent flow, heat transfer, and such solutions. So here we have the fluid flow part. This is the CFD part. And under fluid flow option, we have single phase flow, multi-phase flow. Under them, we have several other options, right? We have porous media, high Mach number flow, particle tracing, fluid structure. So there are lots and lots of options available. Depending on what kind of problem you want to use, you can select something. So this creeping flow is the simplest maybe. It is single phase, just one type of fluid, like just air or just water or just whatever. And then it's very low Reynolds number, like Reynolds number less than 1 or something like that. We call it creeping flow, very, very low Reynolds number. And then we have the laminar flow option. We have the turbulent flow option, rotating machinery, viscoelastic, potential flow. So remember in 305, you studied potential flow, idealized, inviscid, rotational flow. So you can do those kind of solutions also. So today I will just go with the laminar flow option first. Maybe we will do some others if time allows. So two-dimensional laminar flow, I will just press add. So that physics is added. And then I will go to the study part. In the study part, it's about time dependency, whether you want to do a stationary time-independent solution or a time-dependent solution, or other options are also available depending on which physics you're using. So I will go with stationary, time-independent, simple solutions. So the solutions we're going to do today are very, very simple actually. And then I will press done at the very bottom, and then we want to save the changes. So this is my earlier project I was working on. I will just say, no, I don't want to save it. And then let's see. An empty project should be created. I don't know why it is very slow. It's not that slow actually, usually, typically. All right. So this is a two-dimensional laminar flow project that I'm working on. And I will be using this left part, model builder part, and also the settings part. And here I have a graphics window, and down here I have a messages part, and then progress and log and other things, right? So let's clear all the previous messages. All right. So the first thing to do is probably create a geometry, right? And if your geometry is complicated, you can just use a separate CAD software like NX or Fusion, Autodesk Fusion, Siemens NX, or something, whatever your favorite CAD program is. You can create it in that CAD program, and then you can import into a CFD software. But we have also some drawing and CAD functionalities available inside console. And I will be using those available ones today because the geometries I'll be working on are extremely simple, like perfect squares, perfect rectangles, and such things. So here is our textbook, Manson's textbook, and this is the Navier-Stokes chapter. Remember, we started 306 this semester with a review of this Navier-Stokes part. So this is chapter 6, Navier-Stokes, and we did some exact solutions there. So for example, yeah, this problem, we may work on this one. So this is steady laminar flow between fixed parallel plates. So we have two plates. They are both fixed. We have a pressure gradient, dp dx constant, and it is negative. So we establish a flow from left to right, and then we obtain a parabolic velocity profile, laminar flow. We will not be doing any turbulence today, or everything will be laminar, right? So, but this is fully developed. Let's say this channel is not, in our case, it will be like that. It is not infinitely long in the x direction, but it is of finite length. So there will be an entrance at the left side, an inlet boundary, let's say with uniform flow. And then there will be a flow development part. And then there will be a fully developed part. And at the very right, there will be an exit, right? So we will draw a rectangular channel like this with an inlet here, with an exit here, and then two walls. And we will see the flow development effects and the pressure drop, the nonlinear pressure drop close to the entrance, and then linear pressure drop after the entrance region, and so on. And then we can do some numerical calculations and compare like our findings with these exact solutions. Since this is the first CFD problem we are solving, it is very easy to make mistakes. That's why we need to start with the simplest possible problem, and this is simple enough. So with an analytical solution, at least for the fully developed part, right? All right, so, and we know that the Reynolds number should be lower than a certain critical Reynolds number to have laminar flow. So if it was a pipe flow, the critical Reynolds number was like 2,100, 2,300. For this one, channel flow, it is something like that. So if we go with, for example, a Reynolds number of like 1,000 or 1,015, 1,500, and or 1,000, like 2,000 or something like that, we should be fine, right? Right, so we will draw this rectangular geometry. It's just a very simple rectangle. If I go back to console and then I have this geometry part here, if I right click, there is a rectangle option. And then with that rectangle option, so I will just go ahead and check my notes. Here I used a rectangle of height 0.1 meter, right? So it's 0.1 meter height, and then width is 1 meter. And then if I build it, it will be like nice kind of with an aspect ratio of 10, I guess. So we have 0.1 height and 1 meter of length. So it is a rectangle, something like this. All right. That's it. This is our geometry, right? So we will assign a boundary condition of inlet at the left, assign a boundary condition of outlet at the right, and then no slip wall boundary conditions at the top and bottom. And that will be it, right? That will be it. So I will just go to, so this is our flow domain. I will go to the laminar flow. So there are lots of details here. We're not going to use everything. We have global definitions. We don't use that. We have component one. Under it, we have lots of things. We have study one and then results. So if I just make it compact, it is like this: global definitions, not useful for us. Under component one, we will do lots of settings. Study one is the actual solution of the problem and obtaining the results. And the results part is like visualization, looking at the results, like plots and such things. So under component one, we have definitions, not useful for us today. For geometry, we created a rectangle. That's our geometry. For the materials, you can select the material. So there is a built-in material library. We have air, water, different kind of engineering fluids, all common ones. We're not gonna select anything from the library today. And then we have the laminar flow part. And under laminar flow, we have fluid properties, for example. And under fluid properties, it says density and viscosity needs to be specified, right? And I have just one domain. and there is just one fluid. It's very simple. So I will not go with from material option, but instead I will just select user define. When I do that, the default value is 1000 kilogram per meter cube. So it is like the density of, this is the density, this the density of water, almost 1000. I will not change it. And for the dynamic viscosity, I will not go with from material, but I will say user define, and it says 10 to the minus 3. That is again like the viscosity of typical water at kind of standard conditions. I will not change them. They are nice, round, like easy to work with numbers. So 1000 rho, and then mu is 10 to the minus 3. The kinematic viscosity becomes 10 to the minus 6, I guess. So it will be 10 to the minus 6. I maybe need to check something here. Chat'e birileri bir şeyler yazmış. Ekran kaydı meselesi. Okay, we covered. So I think it's recording right now. Yeah, it is recording. Bu arada arkadaşlar, ODTÜ'de burada makine mühendisliği bölümünde bugün ben ofisteydim bütün gün. Sürekli elektrikler kesildi. 2 kere 3 kere belki daha fazla gitti geldi. Gene kesilebilir. Ve kesilirse yapacak bir şey yok. Yani burada bir jeneratör yok. Benim bir UPS'im şu anda çalışır vaziyette yok ve bu kayıt şey olur yani. Bu session biter. Ben bir yere gitmem. Burada dururum. Elektrik gelirse tekrar başlatırım. Artık kim kalmış olursa burada onlarla devam ederiz. But so we have some power outages going on here today at our department, in my office. All right, so fluid properties, we set them, rho and mu, that's it. We don't need anything else. We're not doing any heat transfer, no thermal conductivity, nothing like that. So rho and mu are the only material properties. And then for the initial values, we have just 0, 0 velocity components. We have two velocity components, two-dimensional flow. Pressure is 0 everywhere. So these are typical, useful initial values. And then this is a boundary condition. It says wall 1. And then if you look at it, we have 1, 2, 3, 4. So all these 4 edges are set by default to wall boundaries as wall boundaries, but that's meaningless. We will just change them. So I will go to laminar flow, right click it, and then I will say inlet. So that will introduce an inlet boundary condition. And here I will select the left boundary, and it's the inlet. So its number is 1. So 1 is the left boundary. And then I will specify a U0. So I will again check my notes to see what kind of inlet speed I specify. So I simulated, according to my notes, a Reynolds number of 1000. So Reynolds number is this inlet speed, constant inlet speed, which is the average speed in the channel, times the channel height, which I think I selected as 0.1, divided by the kinematic viscosity, which is 10 to the minus 6. So if you do that math and set the Reynolds number to 1000, I think the inlet speed turns out to be 0.01 meters per second. So U0, the inlet speed, I set it to 0.01 meters per second. At an inlet, you can specify velocity, or you can specify pressure also at an inlet. So you can set a high pressure here at the left, you can set a low pressure here at the right, and then that pressure difference will derive the flow. It can be done in that way also, but I wanted to do it at velocity inlet, pressure outlet kind of. So you can specify mass flow, or you can say fully developed flow. We have different options, different boundary condition options are available. I will go with the uniform constant 0.01 meters per second speed. So again, this 0.01 meter times the height of the channel, which is 0.1, divided by the kinematic viscosity, which is 10 to the minus 6, gives a Reynolds number of 1000. And I think it will be a laminar flow with 1000 Reynolds in this channel, right? And then I will also set an outlet boundary at the right. So I will go to laminar flow again, right click, and we have lots of different options here. Like we have symmetry boundary, open boundary, boundary stress, periodic flow, interior wall, and different options. I will go with outlet. So an outlet boundary condition is introduced, and for that I will select the right one. So its number is 4. And then by default, a static pressure of value 0 is specified there. So when you do incompressible flow simulations, and this is an incompressible flow simulation, the pressure values themselves are not that important. So whether you set here 0 or 10 or 100 or 1000, doesn't matter. Only, oh, your meeting will end in 10 minutes. Why is it the case? Oh, come on.
Because this is the free edition.
What's that?
This is the free edition, so there's a 40 minutes time limit.
But 40 minute geçmedi ki. Sadece 20 dakika geçti. Isn't it? 10 minutes. ODTÜ'nün Zoom şeyi bitmişti. Vardı pandemi döneminde. Sonra bitmişti. So I think we have to just stop and then start again after 10 minutes immediately. So it will automatically end after 10 minutes, and then we will start it again. So you have to log in again, unfortunately. So that's the way it is. So I was talking about pressure and in incompressible flows, only pressure variations, pressure gradients, how pressure changes in the x direction, how pressure changes in the y direction. In other words, dp dx, dp dy. Those are important, not the pressure values themselves. If you remember the governing equations, so what are the equations that we are solving in this CFD simulation? The continuity equation, conservation of mass, and two components of linear momentum equation. And in continuity equation, there is no pressure, only velocity. And for the momentum equations, we have pressure derivatives only, dp dx and dp dy. So that's what matters only in terms of pressure. So that's why you can specify whatever pressure value here. So 0 means, so this is a reference, or it's not an absolute pressure. It is with respect to some other built-in pressure that COMSOL uses. And I believe the built-in pressure is like 1 atm. So when you say 0 here, so with respect to that 1 atm, it is like 0 pressure. In other words, you specify atmospheric pressure at the end. So it's like a channel or a pipe or something which is open to atmosphere or something like that. But like I said, it doesn't matter what value you specify here. And then we have other options not critical for us today. And then if you go to this wall 1, now you see 1 is overridden because we changed the boundary condition here, and then 4 is overridden because we set outlet, and then 3 and 2 are still there as wall boundary. So top and bottom are no slip walls. As you see, it's a no slip wall boundary. So we have 3 types of boundary conditions here: wall at the top and bottom, inlet at the left, and outlet at the right. So that's it, simple, right? And then we need to generate a mesh, right? So if you go to this mesh part and then say build all, it will generate a mesh, a default mesh with default settings. And by the way, COMSOL is a finite element method-based CFD, or not CFD, but like engineering software. It's finite element method-based. When we do CFD, finite element is not the most commonly used, most popular option. The most popular one is finite volume. For example, ANSYS Fluent is finite volume based. Star CCM is finite volume based. OpenFOAM is finite volume based. But COMSOL is finite element based. It's not important. It's not important. You can do it with finite element, finite volume, finite difference. Different methods are there. But COMSOL is finite element based. And these are our elements. So if I zoom in, I just see something like this. So by default, close to the walls, COMSOL put some boundary layer meshes. We call these boundary layer meshes, these nice structured, like layer by layer meshes. It put 2 of those. And then the same thing happens also at the bottom boundary. Here we have 2 layers of boundary layer mesh. Why? Because boundaries and the interaction of the fluid with the walls is important due to heat transfer, due to like shear forces, pressure drops, and everything, right? That's why it created a spatial type of boundary layer mesh close to the walls. And then away from the walls, it preferred like unstructured mesh with triangular cells. So all these are cells. So how many of them we have here? It says 11,400 something. So more than 10,000 domain elements. So the number of elements we have here, all of them is like more than 10,000. The more we have, the more accurate the solution will be, but the more time it will take. So this is the default mesh, right? So we can change this. Since this is a very simple geometry, I can say right click this mesh and then say mapped. And then under mapped, I will say just the entire domain. And then I will say a build all. So when you just go to a mapped mesh option, it tries to just put nicely aligned, structured kind of rectangular or square kind of elements in the whole domain. Since our domain is very simple, just a rectangle, it is possible to map it with these kind of square or rectangular elements. If your domain is more complicated, you cannot do that. But our domain is simple, so we can do it this way. We can do it this way. So, but the resolution may not be enough. We don't have maybe that many elements. The number of elements affects accuracy. I can just right click on mapped and I can introduce a size. And for that size, I can just set maybe a custom size. And then I can say the maximum element size is like, I don't know, I will try something 0.01. So I'm saying that do not generate elements larger than this size. At most, make them this much. And let's say build all. Oh, I didn't enter a small enough value. Let me put one more 0.001 and then build all. Oh, this is too much. So we have lots of elements. It's all black, many elements. How many of them? 100,000 is just too much. I will just go to 5 maybe, and then build all, or maybe, I don't know, 2, 5 maybe. I'm just playing with it, right? I'm playing with it. Of course, we do not typically generate meshes like this, trial and error, but this is a first simple tutorial, so the mesh is not really that much critical. And I am kind of arbitrarily, without thinking too much, generate a mesh. And our mesh is this one here. So these kind of squares, how many of them? 16,000. So we have 16,000 elements. So over each of these elements, maybe at the corners of these elements, also maybe at the centers of the edges and maybe at the midpoint of the elements, we will calculate velocity components and pressures. So in this solution, there will be like more than 10,000 velocity values, U and V velocities, and more than like 10,000 pressure values. Over each element, there will be UV velocity and pressure. Bizim 10 dakikamız kalmıştı. Ne kadar zamanımız kaldı? Bunun bir timer'ı bir şeyi yok mu?
Hocam. Herhalde.
Hı?
Sağ üstte yazıyor hocam 1.45 kalmış.
Nerede? Sağ üstte. Siz görüyorsunuz da ben görmüyorum.
Ha, o zaman olmuyor biraz. 1.35 kaldı şu an.
1 dakika 45, 2 dakikamız mı kalmış?
Aynen 1.5.
Anladım. Peki. All right, so let's make this the first part of today's session and then end it. I will end it and then I will just restart it again and you can come back again with the same like meeting ID and password. And then there will be a couple of parts like this, I believe. So let me just end this part of the session and then I will start it again. So see you again in just 1 minute. Let me stop this share and then end this.